Then another way to determine the nuclear charge radius is from direct measurement of the Coulomb energy differences of nuclei. Consider for an example 3,1H2 and 3,2He1. To get from 3He to 3H, 3H helium to 3H, we must change a proton into a neutron. There is a strong evidence which suggests that the nuclear force does not distinguish between protons and neutrons. Okay, both particles have they can feel the same nuclear force. Changing a proton into neutron should therefore not affect the nuclear energy of the three nucleon system. Only the Coulomb energy should change because the two protons in 3He experience a repulsion that is not present in 3H. The energy difference between 3He and 3H is thus a measure of the Coulomb energy of the second proton, and the usual formula for the Coulomb repulsion energy can be used to calculate the distance between the protons and the size of the nucleus. Only protons can feel the Coulomb force. Neutrons and protons, they feel the nuclear force. So since the protons are charged particles. The situation is resolved if we choose a case as 3He, 3H in which no change of orbital is involved. That is, in which the number of the last proton that makes the change is identical to the number of the last neutron after the change. The Z, the number of protons of the first nucleus, must equal the number of neutrons of the second, and thus the N of the first equals the Z of the second. Such pairs of nuclei are called mirror nuclei because one is changed into the other by reflecting in a mirror that exchanges protons and neutrons. Examples of such pairs of mirror nuclei are 13,7N6, 13,6C7, or 29,20Ca19 and 39,19K20. The Coulomb energy of a uniformly charged sphere of radius r is Ec equal to 3 by 5 1 by 4 pi epsilon 0 q by q square by r. Ec equal to 3 by 5 1 by 4 pi epsilon 0 q square by r, where q is the total charge of the sphere. അപ്പോൾ ഇത് എങ്ങനെ സോൾവ് ചെയ്തെന്ന് ചോദിച്ചു കഴിഞ്ഞാൽ നമുക്ക് ഗ്രിഫിത്തിൻ്റെ ഇലക്ട്രോഡൈനാമിക്സിൻ്റെ പുസ്തകത്തിൽ നോക്കിക്കഴിഞ്ഞാൽ നിങ്ങൾക്ക് അവിടെ ഇതിൻ്റെ ഡെറിവേഷൻ നിങ്ങൾക്ക് കാണാൻ പറ്റും. ഇതുപോലെ ഒരു പ്രോബ്ലം അവിടെ ചെയ്തിട്ടുണ്ട്. The difference in Coulomb energy between the mirror pair is delta Ec equal to 3 by 5 a square by 4 pi epsilon 0 r Z square minus Z minus 1 whole square. അപ്പോൾ ഇതിൻ്റെ ഡിഫറൻസ് എടുത്തിട്ട് ചെയ്യുന്നത്. Okay, H is equal to 3 by 5 a square by 4 pi epsilon 0 r into 2Z minus 1. Since Z represents, ഇവിടെ കൺഫ്യൂഷൻ ഉണ്ടെങ്കിൽ ചോദിച്ചോളൂ. Since Z represents the nucleus of higher atomic number, the N of that nucleus must be Z minus 1, and so A equal to 2Z minus 1 with R equal to R equal to R0 A per 1 by 3. Therefore delta Ec equal to 3 by 5 E square by 4 pi epsilon 0 R എന്നുള്ളത് സബ്സ്റ്റിറ്റ്യൂട്ട് R0 A power 2 by 3. ഇവിടെ നമ്മൾ A കൊടുത്തിട്ടുണ്ട്, അത് സബ്സ്റ്റിറ്റ്യൂട്ട് ചെയ്ത് അങ്ങനെ കിട്ടും. These Coulomb energy differences can be directly measured in two ways. ഈ ഡിഫറൻസ് കണ്ടു കഴിഞ്ഞാൽ നമുക്ക് റേഡിയസ് കണ്ടുപിടിക്കാൻ പറ്റും. One of the nuclei in the pair can decay to the other through nuclear beta decay, in which a proton changes into a neutron with the emission of a positive electron or positron. The maximum energy of the positron is a measure of the energy difference between the nuclei. Second method പറഞ്ഞിട്ടുണ്ട്. The measured energy differences are plotted against a power 2 by 3. ഇവിടെ ഒരു ഫിഗർ കാണിച്ചിട്ടുണ്ട്. as expected from the equation on the previous the dependence is very nearly linear. The slope of the line gives r0 equal to 1.22 femtometer. X-axis a power 2 by 3, y-axis delta ECM ഇവ ചെയ്ത് കഴിഞ്ഞാൽ സ്ട്രെയിറ്റ് ലൈൻ കിട്ടും. ആ ഇക്വേഷൻ അപ്ലൈ ചെയ്ത് കഴിഞ്ഞാൽ ആ സ്ലോപ്പ് കണ്ടാൽ നമുക്ക് r0 കിട്ടും. r0 from this experiment r0 is found as 1.22 femtometer. അപ്പോൾ ഓരോ ടൈപ്പ് എക്സ്പെരിമെൻറ്റിൽ നമുക്ക് r0 ചെറിയ വേരിയേഷൻ കാണാൻ പറ്റുന്നുണ്ട്. Even though these measurements of the nuclear charge radius are very different techniques. Charge radius use very different techniques. They all give essentially the same results. The nuclear results varies with mass number as r0 a power 1 by 3 with r0 varies 1.2 to 1.25 femtometer, right?